Welcome, curious minds, to another deep dive. In today's, hyper-accelerated tech landscape, the sheer volume of information on modern system design can feel less like a stream and maybe more like a tsunami, right? Developers, senior engineers, you aspiring solutions architects, you're constantly trying to keep pace with new frameworks, patterns, best practices. It's incredibly easy to get swept up in the noise. But our mission today, really custom tailored for you, is to cut through all of that, distill the signal from the noise, and deliver those impactful aha moments that genuinely accelerate your understanding. Our source material for this deep dive is truly exceptional. Key excerpts from Spring System Design and Practice. Now, this isn't just theoretical musings or, high-level academic concepts. No, this book is packed with practical, job-ready understanding. We're talking about the kind of insights that you can directly apply to building robust, scalable systems in the real world, maybe even starting tomorrow.
That's precisely our goal. We want to extract the most important nuggets of knowledge from each section, focusing on core concepts, walking you through real-life industry scenarios, dissecting the practical trade-offs you'll inevitably face, and really laying bare the architectural reasoning behind crucial decisions. And to keep it all grounded, to give us a tangible example to follow, the Home at Startup case study, which is central to the book, will be our guiding thread through these often complex topics.
Exactly. So settle in. We're aiming for a conversational, engaging tone, like a friend sharing cool new insights they just discovered. But with all the depth and rigor you'd expect from seasoned guides, we're essentially joining the Home at Startup team today, embarking on building their system from the ground up, chapter by chapter. Okay, let's unpack this journey into resilient and scalable system design. So if we're building Home at from scratch, where do we even begin? The book hits us with a foundational truth that's, often overlooked but utterly critical, truly understanding product requirements. It's a step that, surprisingly, many teams rush past, eager to jump into code. But the book really emphasizes that this is the foundational step in any system design. We're talking about delving deep into the what and why before you even think about touching a line of code. It's not just about what the system will do, but what fundamental problem it solves for its users.
What's truly fascinating here, and a core aha moment the book delivers, is how it frames this initial phase. It's all about transitioning from a customer's current problem state to an envisioned solution state. Think about the social media example the book uses. Before platforms like Facebook or Instagram, people experienced communication gaps, right? A lack of instant connection with distant friends and family. The problem state was fragmented relationships, isolated moments. The envisioned solution state, instant, effortless connections, shared experiences in real time. Social media didn't just add a feature, it fundamentally changed how people interact, bridging a previously unrecognized, almost subconscious need. That's the depth of problem understanding you really need. And this leads to a key principle that often trips up even experienced teams: the crucial distinction between high-level business requirements and technical requirements. Business requirements must focus squarely on what the system should accomplish, on the user value, not how it should be implemented.
If your requirements document right from the start begins prescribing the use of, say, a specific database technology like Postgres, or maybe a particular architectural pattern like microservices, you've immediately limited innovation. You've boxed in your development team. This can inadvertently trap them into narrow solution paths, preventing them from exploring and discovering potentially better, more optimal, or even simpler choices later on. The moment you define the how and the requirements, you stop truly thinking about the what and the core problem you're trying to solve. That's the real insight here. Premature technical specification kills innovation.
That what, not how distinction makes so much sense. I've personally seen teams fall into that trap, and it's like trying to build a house when the client's only specified a nice warm home, but your architect's already chosen the brick supplier. But if you do get those initial requirements wrong, if you miss a critical what or bake in the wrong how, what are the first practical headaches that typically hit an engineering team?
Well, the biggest one, and the book underscores this powerfully, is technical debt. We're talking about things like code lacking automated tests, poorly designed software, maybe inefficient delivery pipelines. This debt directly impacts the user journey. It manifests as performance issues, where processes slow down to the point of user abandonment, or data inconsistencies, leading to user frustration and a breakdown of trust, or simply poor usability, making interfaces unintuitive or non-functional. In real companies, there's this constant gnawing tension between churning out shiny new features and repaying that technical debt. Prioritizing features over addressing underlying issues is a common trap, but it will eventually catch up with you, impacting user experience, maintainability, and ultimately the business's bottom line. Another massive red flag is vague documentation. If your requirements documents offer nothing more than high-level business goals, that's a significant development risk. You need clear written statements of expectations. Without them, you risk rampant misinterpretation, wasted development effort, and severely delayed delivery. This is especially true when product teams only provide visual representations without explicit business rules. Developers might find that those visuals imply business rules not stated, or that they inadvertently lead to performance issues when implemented at scale.
So clarity is absolutely king, both in what you're building and why. What about anticipating things going wrong? It's not always sunshine and rainbows in production, is it? We've all been there.
Absolutely not. The book emphasizes the critical importance of planning for bad days or exceptions. What if there's a hiccup in system performance? What if a third-party service Homeit relies on temporarily goes down? Good requirements anticipate and plan for these less-than-ideal scenarios from the start. This proactive approach ensures a much more resilient system, as you've already considered how it should respond to unexpected events. Whether that's seamless recovery without the customer even noticing, or gracefully redirecting users to a customer support team with clear instructions, it's about designing for failure, not just success. And finally, a holistic view is non-negotiable. Product managers sometimes provide requirements that disregard other business areas or processes within the organization, but system design must consider the broader organizational context. If a new Homeit feature impacts the finance department's reconciliation process, or maybe the legal team's compliance obligations, those interactions need to be deeply understood and explicitly accounted for in the requirements. Ignoring this can lead to friction, rework, and suboptimal outcomes across the entire organization, turning a seemingly good feature into an internal headache.
This all ties into thinking about the future, doesn't it? Beyond just fixing today's problems, how do you ensure you're scaling results in line with long-term business requirements? Because Homeit, like any startup, has big ambitions.
Precisely. This is where truly strategic system architecture comes into play. It shouldn't just be built for today's immediate needs. A robust architecture needs to anticipate the next 5 to 10 years. The core question for Homeit's engineers becomes, does my architecture provide a general, adaptable approach for facilitating these future requirements? This prevents engineers from constantly creating ad hoc, one-off code for similar use cases, which is an incredibly common and inefficient scenario when long-term thinking is overlooked.
And the book encourages asking some really pointed questions to get that long-term thinking started. Things like, what new types, levels, or products will be created in the next 5 to 10 years? How much sales growth is expected? Which new geographies are targeted? How many more use cases are anticipated? For Homeit, if the goal is to scale to 30-plus countries, your initial architectural decisions on, say, data localization or payment gateways absolutely need to support that, right? Without that foresight, you find yourself rewriting or patching things after the fourth similar use case has been released, losing significant time and money.
Exactly. It's about building a robust foundation that can adapt and expand gracefully, not constantly patching a house of cards. And when it comes to evaluating new features, prioritization is key. The book outlines 3 critical criteria that every product team should rigorously apply. First, problem intensity. Is the problem significant enough that it truly motivates users to seek and adopt a solution? If it's merely a minor inconvenience, the feature might not get any traction. Second, market size. Will the feature reach or attract a large, valuable audience? A feature that solves a widespread, impactful problem will naturally appeal to more users. And third, frequency of use. Can the product integrate into users' daily activities, leading to frequent engagement, or is it just a one-time solution that users forget about? You, as a senior engineer or solutions architect, should challenge product teams with tough questions about whether a proposed feature truly solves a clear, intense problem and aligns with the long-term vision. This critical scrutiny prevents wasted development effort on irrelevant features that don't contribute meaningfully to the company's objectives or genuinely address customer needs.
Okay, so summing up this first deep dive, the key takeaway is crystal clear. System design truly starts with deep, structured thinking about the what and why of the product, not just rushing to the how. But Homeit has a big vision. Once you have that big picture, the real challenge begins. How do you break that grand vision down into actual, tangible pieces that a team can build? That's where the next part of the book really shines.
Sorting complex requirements into features, use cases, and stories.
So we've helped Homeit nail down their big vision and understand the overarching product requirements. But how do you go from a grand idea to something a development team can actually implement? The next step, as the book details, is to bring order and specificity to those requirements. It's about structuring them so they can truly be translated into functioning software.
Right. This section is all about deconstructing the system's elements to truly enable the customer's journey. You start by identifying the core components that interact with your system, actors. Who interacts with the system? For Homeit, that's clearly tenants, landlords, and realtors. Understanding their distinct roles is foundational. Events. These are the critical actions users perform, like signing up, searching for a property, making a rental offer, handling payments, or maybe cancellations. Each event is attributed to a specific feature, helping you delineate responsibilities. Life cycles. This is where things get interesting. It's the progression of an object across different levels or stages over time. Think of a Homeit rental proposal, moving from open to approved to payment processed. Visualizing these leads directly to state diagrams, which become absolutely crucial artifacts for developers to understand transitions and, critically, for mapping accurate test cases. Stages. These are simply distinct phases within a life cycle. Types. Different classifications of objects such as a rental property type like apartment, house, condo. Levels. Ascending layers that distinguish valuable behaviors, often creating quality tier systems. The book uses the excellent example of lower insurance prices for high-quality rental properties, which encourages landlords to maintain their properties. This distinguishes and rewards valuable behavior programmatically. And loops. Repetitive processes within the system, like a tenant repeatedly searching for properties. These elements provide a precise blueprint for the real structure of your system before you write any code. Building on that, the book introduces user journeys as a powerful way to visualize user behavior over a long time frame, making the entire user lifecycle explicit. It contrasts them with critical events by explaining that user journeys illustrate larger chunks of actions, like home, its entire rental process, while critical events delve into the finer, granular details within those journeys.
And Homeit provides great examples here. For instance, the tenant user journey would summarize actions like searching for properties, scheduling visits, making offers, and paying rent. It's the full narrative. On the flip side, the landlord user journey would cover managing properties, reviewing offers, and accepting payments. It's like creating a narrative arc for how different users experience the Homeit system from start to finish.
Precisely. Then we move into user stories. The core concept here is conveying requirements from the user's perspective, fostering empathy within the team. The template is simple, yet incredibly effective. As a type of user, I want some goal so that some reason benefit. This structure forces everyone, product, design, engineering, to focus on user needs over technical intricacies, forming what the book calls the backbone of the system. It genuinely helps colleagues wear the user's hat and ensures the team is building what truly matters. And finally, use case descriptions. These combine all the previous tools to provide a clear, comprehensive perspective of how a feature should work, acting as the canvas for expressing software intent. A crucial element within use cases, often underestimated, is triggers. Triggers are the specific context that enables a user to initiate an action. Take the home rental property search, for example. If triggered from a mobile phone, the feature might intelligently leverage GPS to find nearby properties. If triggered from a personal computer, a larger screen layout with grid views might be more appropriate. It's vital to understand that different triggers can lead to different sets of critical events within the same use case, profoundly impacting how the feature is designed and implemented. Overlooking triggers can lead to a brittle, inflexible system.
That's a great point about how context can change everything. So once you've methodically identified all these pieces and their interactions, how do you structure the final business requirements document for actual development? Because a messy document leads to messy code, right?
Right. The book discusses the strategy of phased releases, launching simplified versions first to get value to users faster and gather feedback. For example, home. It could start with a landlord flow release, focusing only on landlord registrations and property listings, with tenants just being passive visitors initially. Then, a subsequent tenants flow release would activate tenant-specific features. Requirements documents are agile and evolve for each release, ensuring focus and iterative delivery. Another crucial aspect, especially for robust high-volume systems, is anticipating alternative behaviors. Programmers absolutely need to understand how to handle unexpected user actions or bad scenarios. It's vital to ask, what if the user behaves differently at point X, and how should the system respond? This includes considering nuanced recovery strategies. Should it be seamless recovery without the customer even being aware of the underlying failure, or should customers be gracefully redirected to a customer support team with specific instructions? This proactive planning is truly essential for resilient systems that can handle the chaos of the real world.
Ultimately, the relationship between features, use cases, and user stories forms a potent artifact hierarchy. This structured approach transforms abstract business needs into a concrete, actionable technical vision. It's about laying the groundwork for development effectively, ensuring everyone on the team has a shared, precise understanding of what they're building and why.
So what does this all mean for building Homit's system? It's clear that getting from that big idea to a concrete plan requires a meticulous, structured approach to requirements. It's the difference between building a sprawling, unmanageable system and one that's well-defined and ready to scale. And with those requirements nailed down, the next logical step for Home is to start thinking about the actual components that will form the system.
Defining domains for your application.
All right, we've covered understanding Homit's requirements and structuring them into actionable pieces. Now, for the critical step of organizing the system's core building blocks, domains. This introduces the fundamental concept of domain-driven design, or DDD. As the book points out, a foundational text here is Eric Evans's classic domain-driven design tackling complexity in the heart of software. It's a paradigm shift in how you think about architecture.
The very first step in domain modeling, and an incredibly insightful one from the book, is what it calls detecting common concepts and eliminating redundancy. This isn't just an abstract exercise. It means rigorously identifying frequently appearing nouns or substantive terms across all your Home history, use cases, conversations, and requirements. These recurring terms are not just words. They are strong indicators of distinct domains. For Homeit, the book illustrates this beautifully. You'll quickly identify a tenant's domain, a landlord's domain, and a rental proposal domain. This initial, almost intuitive identification simplifies the early steps of domain modeling, laying a clear conceptual foundation that aligns directly with your business language. The aha here is realizing that those simple nouns are your future-bounded contexts, your microservice boundaries waiting to be discovered, preventing painful refactors down the line when you realize you've mashed together unrelated concerns. Next, you move into setting up domain composition, boundaries, and limits. This phase is often more philosophical than purely technical, leading to extensive and sometimes heated discussions within a team. The central question is, should a domain become its own independent microservice, or should it merely exist as a property of another larger domain? These discussions directly influence your architectural choices, particularly the granularity of your microservices. Ideally, a single microservice should represent one bounded context and one cohesive domain. However, sometimes a domain might start as a subdomain within a larger microservice for pragmatic reasons. It's a constant trade-off between strict separation for ultimate independence and pragmatic grouping for initial development velocity. The book strongly warns against falling into the red zone of multi-monoliths, where you get bloated, hard-to-manage code spread across multiple servers without the benefits of true microservice independence.
That sounds like a constant negotiation, finding that perfect balance. So once you've defined these domains and their boundaries, how do you represent their operations and actions, especially when you start thinking about APIs? It's not just about the data, is it?
This is a critical point that many developers, even experienced ones, often fall short on. The common trap is only representing basic objects like products or customers and their APIs, fixating solely on mapping tangible resources to database tables. But it's equally, if not more, important to explicitly model operations and actions for each domain, not just the tangible resources. For Homeit, you wouldn't just have a rental proposal object, you'd explicitly model actions like accept rental proposal or reject rental proposal. Failing to do so can lead to confusing and bloated code later, where business logic related to actions is scattered, awkwardly shoehorned into resource-centric APIs, or leads to a transaction script anti-pattern. You need to model what happens to the objects, not just the objects themselves. When it comes to modeling and documenting these domain services correctly, the book outlines 4 essential steps, providing a clear blueprint. 1. Basic actions, CRUD. First, define the fundamental failure. Create, read, update, and delete operations for your domain. These are the absolute building blocks, the minimum required interactions. 2. Business actions. Beyond simple CRUD, define operations specific to the domain's unique business logic. For example, in a partnership proposal domain, you'd have distinct actions like send proposal, accept proposal, or reject proposal. These encapsulate the core behaviors of the domain. 3. Messaging and interactions. Consider how the domain interacts with other systems. Does the partnership proposal domain need to send messages to users upon acceptance, or maybe store messages as child objects for historical record? This ensures you account for the broader system context and asynchronous communication needs. 4. security, and authorization. Critically, how are actions within this domain secured? Who can perform them? This integrates security considerations from the ground up, not as an afterthought.
It sounds like a truly holistic approach to defining what a domain does, not just what it is. And the book mentions sequence diagrams as an exceptionally key tool here. What's so important about them in this phase?
The rental proposal sequence diagram for Homeit in the book is a prime example of their immense importance. I found them exceptionally effective in visually explaining complex system flows, specifically how information passes between different services. They foster critical team collaboration, ensuring everyone is literally on the same page about interactions and dependencies. They also become key artifacts for developers, enabling accurate test case mapping because you can see the precise order of operations. For Homeit, the complete rental flow sequence diagram illustrates core system operations, showing not just direct calls but also implicit notification exchanges. Observing this, you can immediately identify the need for a new notification domain, for instance, because it's clearly a cross-cutting concern used by many services. These diagrams help new domains emerge naturally from the system's interactions, not from an arbitrary decision.
So this section truly reinforces the power of domain modeling in creating well-structured, maintainable, and ultimately scalable systems. It's really about taking those abstract business requirements and giving them a logical, actionable structure that developers can build upon. That clearly sets the stage for what comes next, making the actual technology choices.
Defining services for your domains.
We've built a strong conceptual foundation for Homeit by deeply understanding product requirements and meticulously defining our core business domains. Now, for many engineers, this is where the excitement really builds. We transition to the practical considerations of selecting technologies and actually defining our services. This is where we move beyond abstract concepts to the underlying infrastructure that will bring Homeit to life.
This is precisely where non-functional requirements, NFRs, take center stage, and the book emphasizes their paramount importance. NFRs, things like performance, scalability, security, availability, and maintainability, heavily influence every single technology choice and architectural decision you make. They answer the crucial question of how well the system must perform, beyond just what it does. To truly understand them, you need to ask a lot of nuanced questions. For instance, let's look at some key questions for NFR assessment that the book highlights, and think about their implications for Homeit. User interaction. How will users primarily interact with the Homeit system? Is it mainly mobile, desktop, web, or maybe API-driven for partners? This dictates so much. If it's heavy on mobile, you might prioritize protocols optimized for low bandwidth, or consider serving search results in formats easily consumed by mobile apps. If desktop users prefer to export data, you might need CSV output for Excel. For Homeit, thinking about mobile users searching for nearby properties via GPS immediately tells you you'll need geospatial indexing capabilities in your database. Data characteristics. This is a goldmine for NFRs.
What's the expected data volume? For properties, users, proposals, what kind of data are we dealing with? Text descriptions, high-resolution images, videos for virtual tours. Is location-based, georeferenced data paramount for home? Its search functionality? How many different entities or business objects are there? What's the best data structure for something like home? Its property search feature, a simple list, a complex map, a graph. Are we generating combinations or permutations of property features automatically? All these questions profoundly inform your data storage strategy and choice of database. Access patterns and protocols. How will data be accessed? Will there be many concurrent reads or writes to property images? Which network protocols will be used? Standard HTTP or perhaps GraphQL for flexible client queries? Is a powerful full-text search needed for property descriptions? What kind of sorting and querying patterns exist? For Homeit, this could mean optimizing for rapid queries around ZIP codes, street names, or specific amenity filters, or sorting rental properties geographically. These patterns directly point to specific database indexing strategies and API designs. Scalability and resilience. How many concurrent users or requests are anticipated for Homeit? For its image processing service, for instance, how many landlords will try to register new properties and upload images concurrently? You absolutely don't want that to become a bottleneck. And critically, what are the disaster recovery DR capabilities? If Homeit's primary data center building burns down or servers are hacked, can key systems remain operational or recover quickly? What are your recovery time objectives, RTO? How fast must systems recover? And recovery point objectives, RPO, how much data loss is acceptable? These questions are often overlooked until disaster strikes, but they're paramount for any production system, influencing everything from data replication to multi-region deployments.
That's a huge, exhaustive list of questions. It really underscores how diverse the needs can be and how easy it is to miss some of these until you're deep into development. What's fascinating here is how your data requirements drive your technology choices. It's not about picking the trendiest tech, but the right tech for the job.
Yes, exactly. The book provides an excellent overview of various storage types and their use cases, emphasizing that the choice is never arbitrary, but a direct consequence of those NFRs. Relational databases, SQL. Think PostgreSQL or MySQL. These are incredibly strong on data integrity, supporting robust transactions and complex relationships. They're ideal for financial transactions, medical records, or home intake. It's core rental proposal data where consistency is paramount. No SQL databases. These offer more flexibility depending on the specific need. Key value stores like Redis or Memcached are blazing fast for caching and speeding up access to critical, frequently read data. Document-oriented databases like MongoDB offer flexible schemas, useful when your data structure might evolve frequently, perhaps for home. It's varied property amenities. Graph databases like Neo4j are perfect for modeling complex relationships, perhaps for understanding connections between users, properties, and contracts in a sophisticated home ecosystem. Time series databases like InfluxDB excel at handling time-based data, useful for tracking property view trends over time. File systems. Something like NFS, Network File System, can be used for shared access to heavy files or large binary objects, effectively treating large objects like local directories. Content Delivery Networks, CDN. For static files, if home needs blazing fast, low-latency delivery of property images or video tours to users globally, a CDN is absolutely essential. It caches content closer to the user. Device data storage. For restricted hardware devices or offline mobile capabilities, Squite or Realm are excellent lightweight solutions for local data. Analytics tools. For large-scale batch processing of historical data, Hadoop is an option. For very fast processing of real-time data streams and complex analytical queries, Apache Spark is the go-to. If you just need a traditional data warehouse for large report data, you'd choose something like Snowflake or Amazon Redshift. The key takeaway is this. The choice of database, file system, or analytics tool is a direct consequence of your specific functional and non-functional requirements. For example, if home needs real-time analytics on property views to see how popular a property is, Spark would be chosen over Hadoop due to its streaming capabilities. If they need to quickly serve property images globally with low latency and high availability, a CDN is indispensable. These aren't just features. They're critical enablers for the system's performance and the overall user experience.
So, defining services means thinking deeply about data, access patterns, user expectations, and resilience far beyond just, where do I put this data? This comprehensive understanding directly informs the selection of Spring projects and other technologies down the line. It's about setting yourself up for success from the infrastructure level up.
Writing your services, introducing REST APIs with the Spring framework.
All right, we've talked requirements, domains, and even picked out our tech stack conceptually for Homeit. For many of us, this is where the impatience sets in. Can we just code now?
Yeah.
And thankfully, this chapter does exactly that. The book essentially says, all right, you've done the hard thinking, now let's build. This section bridges the gap from all that meticulous product and system analysis straight into practical Spring service implementation. It's where the rubber truly meets the road.
Indeed. The first step after that thorough domain design is making the decision on how many programs or microservices are truly needed based on your domain diagram. The book discusses the spectrum from a monolithic application, a single large code base, to a fleet of independent microservices. It also wisely highlights the red zone that all architects should actively avoid, a multi-monolith architecture. This setup gives you the worst of both worlds: bloated, difficult to manage code across many servers, without the benefits of true microservice independence and agile deployment. The decision between a monolith and microservices always depends on your specific functional and non-functional requirements. But the point is to avoid that red zone where systems are overly coupled and hard to evolve. Before diving into Spring specifics, it's crucial to cover HTTP protocol fundamentals. Most modern backend services today are built on HTTP. So we need to understand its core language, HTTP verbs methods. These define the action you want to perform on a resource. Get, retrieve data, post, create new resources, calling Dordal stations, patch, partially update a resource, patches, delete a moving resource. Knowing when to use each is fundamental to building a clean API. HTTP status codes. These are the server's way of summarizing the result of your request. Common ones you'll live and breathe are 200 OK success, 201 created, resource successfully created, 204 no content, request successful, no content to return, 400 bad request, client error, malformed request, 401 unauthorized, unauthenticated, Client needs to log in. 403 forbidden, authenticated but no permission. 404 not found, resource not found. 500 internal server error. 502 bad gateway. The book even humorously suggests the HTTP Cat's website for a quick visual reference, both informative and genuinely fun. Headers and payloads. Headers structure the request, e.g. host, content type, user agent, cache control authorization. Payloads contain the actual data being sent or received. While any data type is technically possible, JSON is the undisputed standard for REST APIs today, being easy for humans to read and machines to parse. A simple curl ip-api.com command in your terminal gives you a real-world example of a clean JSON response.
So HTTP is the language, and RESTful standards are the grammar that makes it coherent. Why do we need these standards anyway? Why not just make up our own URLs and methods?
That's a great question, and it gets to the heart of what REST, or Representational State Transfer, provides. Created by Roy Fielding in 2000, REST proposes a uniform, standard way to organize actions, verbs, on resources, nouns. It provides a predictable, consistent interface that makes APIs easier to understand, consume, and build clients for. The book touches on the Richardson maturity model for RESTful APIs, which offers a useful spectrum. Level 0. Remote procedures. This is the anti-pattern, using arbitrary URLs reflecting operations, like create a rental property. It leads to unstructured and confusing APIs. Level 1, resources. APIs begin to revolve around named resources, like rental properties. Level 2, HTTP verbs. This is where the book primarily focuses, advocating the correct use of get, post, put, delete on those resources. This is the sweet spot for most modern microservices. Level 3, hypermedia controls ADIOs. The highest level, where responses include links to related actions, making APIs self-describing. The key principles of REST are resources, nouns you operate on; statelessness, each request is independent with no server-side session, meaning all necessary information is in the request itself; and a uniform interface, standard HTTP methods. That principle of statelessness is especially crucial for distributed microservices, as it avoids complex server-side session management, prevents race conditions, and simplifies horizontal scaling by allowing any instance of a service to handle any request.
That brings us to Spring itself. How does Spring fit into this, and what are some of its core internals that make building these services so efficient?
At its heart, Spring relies on Spring Beans and the IOC version of control container, specifically the application context. This is where Spring manages all the key objects in your application, your beans, and automatically handles their dependencies through dependency injection. You simply declare where you want a bean to be injected, perhaps as a constructor argument, and the framework takes care of creating and providing the correct instance. This magic of dependency injection is central to how Spring works, promoting modular, testable code. When it comes to building web services, Spring offers two main flavors: Spring Web, servlet-based, and Spring Web Flux, reactive. Spring Web is the traditional, widely adopted choice for REST APIs. It's fast and offers low latency, but historically it used a blocking I/O model, meaning it blocks one thread per request. This can be an issue with very high concurrency or long-running I/O operations like database access or calls to other remote services as threads sit idle waiting. Spring Web Flux, on the other hand, uses a non-blocking asynchronous I/O model. This makes it ideal for thousands or even tens of thousands of concurrent requests or very long I/O operations, as threads are shared across many requests. However, and this is a significant development the book highlights, Java's recent introduction of virtual threads can make Spring Web perform much closer to WebFlux for many workloads. This is a game changer. So the architect's choice becomes less about a fundamental paradigm shift to reactive programming and more about, do we really need the absolute bleeding edge of concurrency and resource efficiency that WebFlux offers for Homeit? Or can we leverage the simpler, more traditional Spring Web model with its new capabilities provided by virtual threads? The book implicitly suggests that for many thousands per second use cases, Spring Web plus virtual threads could be your pragmatic sweet spot, avoiding the learning curve and mental model shift of reactive programming unless truly necessitated by extreme I/O workloads. This is a crucial trade-off for current system designers.
So given all that, what does creating a RESTful API in Spring actually look like in code? What are the key tools Spring provides to quickly get Homeit services up and running?
Spring makes it incredibly intuitive. You use powerful annotations that map your code directly to HTTP endpoints. At REST controller, which combines that controller and a response body. At request mapping, to map HTTP requests to handler methods. And specific method-level annotations like at get mapping, at post mapping, at put mapping, at patch mapping, and at delete mapping to clearly define your API endpoints and their HTTP methods. Input validation is absolutely crucial for robust APIs, and Spring handles it beautifully with @valid used at request body parameters. You simply annotate your DTOs, data transfer objects, with standard validation constraints like at not null, at node empty, or at size. Spring then automatically validates incoming JSON payloads. If validation fails, it immediately returns a 400 bad request to the client with clear error messages, saving you from writing mountains of boilerplate validation code. For generating unique identifiers in distributed systems, the book emphasizes UIDs, universally unique identifiers. These are incredibly important because they allow you to generate unique IDs without needing a central authority or a database sequence. This is perfect for microservices, as different services can create unique IDs independently, avoiding collisions and simplifying distributed data management. And finally, for building a professional API, standardizing error responses is vital. Unhandled exceptions can lead to inconsistent and unhelpful error messages for remote clients, making debugging a nightmare. Spring's solution is at controller advice to define global exception handlers and at exception handler methods to catch specific exception types. The problem detail class introduced in Spring 6 is key here. It's a standardized return object for error payloads, ensuring clients receive consistent, well-formatted error messages, even for unexpected 500 internal server errors, providing details like a timestamp and an instance URI. Beyond writing the code, automated testing with Spring Test is also built right in. The book stresses this: you should never leave tests out of your plans. Manual testing is simply unsustainable and error-prone in complex systems. It discusses unit, integration, and end-to-end tests, and the simple yet fundamental arrange, act, assert pattern.
Spring's Mocking Big C is a fantastic tool that allows you to simulate HTTP requests in your test without needing a running server, letting you effectively test your controllers. You can perform GT, POST, PUT requests, and then assert status codes, inspect headers, and verify JSON paths for successful operations as well as validation failures.
What's fascinating here is how Spring provides the tools to take those abstract design ideas and turn them into concrete, testable services, making the development process so much more efficient and reliable. It's like having a well-oiled machine for building APIs.
Translating business requirements into well-designed Spring APIs.
We just saw how to produce robust HTTP interfaces with Spring. Now let's go a layer deeper. The book then explores the critical pieces of a well-structured Spring microservice, the internal blueprint that allows it to grow gracefully over time and remain maintainable. It's about building for longevity.
Exactly. This chapter is all about mastering that internal blueprint for any Spring microservice, focusing on a layered architecture. It's elegantly divided into 3 horizontal layers, demonstrating a clear separation of concerns, which is fundamental to good design. The objects layer sits at the top. Crucially, the book emphasizes a specific need to separate data structures based on their distinct purpose. For HOMIT, you'll have network data representations. These are what clients consume and send, typically JSON objects for REST APIs. Their structure might be optimized for external consumption. DTOs, data transfer objects. These are plain Java objects used for transferring data across internal layers of your application. They often have simple methods for applying basic business rules or validations within the service itself. Entities. These are objects specifically designed for persistence in a database. They might have JP annotations and be optimized for database mapping. The aha here for architects is understanding that while these structures might represent the same core business concepts, like a rental property, they have fundamentally different needs, validations, and lifecycle stages.
Their separation is vital for a clean, maintainable, and adaptable design, preventing tightly coupled code. The interfaces layer sits in the middle. This layer defines the available methods throughout the application, stripped entirely of their concrete implementations. In Java, this typically means interface classes. For example, rental property service interface. Why? It aggressively promotes loose coupling, making it significantly easier to swap out different implementations. For example, changing from a SQL persistence strategy to a NoSQL one, or using a different caching mechanism without affecting the consumers of that interface. It decouples the what, the service contract, from the how, its implementation. The implementations layer forms the bottom. This layer contains the actual code that provides the concrete logic for the interfaces defined above. This is where the real work happens. The concrete classes, for G, rental property service simple, that contain the business logic, interact with databases, and make the system function. And tying all this together, making it seamless, is Spring's intelligent beans management. The IOC container automatically finds and injects the correct interface implementations, your beans, at runtime. You, as the developer, simply declare your dependencies on interfaces, and Spring takes care of providing the concrete instances, simplifying your code dramatically and promoting true modularity.
That layered approach sounds like it really helps organize complex applications into manageable pieces. But what about when things inevitably go wrong? How do you standardize exception handling to provide consistent, helpful error messages to remote clients? Because inconsistent error messages are a nightmare for anyone consuming an API.
Standardized exception handling is absolutely crucial for any production-ready API. Unhandled exceptions, or exceptions handled inconsistently, can lead to vague, unhelpful error messages for remote clients, making debugging a nightmare for both sides. The solution lies in using Spring's at-controller advice. This annotation allows you to define global exception handlers for your entire application. Within an at-controller advice class, you use at-exception handler methods to catch specific exception types. For e.g., a legal argument exception, resource not found exception. The problem detail class, which we mentioned earlier, is key here, providing a standardized return object for error payloads, ensuring clients receive consistent, well-formatted error messages. For Homeit, imagine you have a rental property controller endpoint that, due to some bug, purposefully throws an unexpected internal error. A sample exception handler class annotated with at-rest controller advice can catch this. It would then provide a customized 500 internal server error response, consistently formatted with problem detail. This response would include specific details like a timestamp, an instance URI, identifying which service instance handled the error, and a custom title and detail message, perhaps. An unexpected error occurred processing your request for rental properties. While it's technically possible to have multiple at-rest controller advice classes, a single one is often sufficient for clarity and ease of management, unless your application requires highly complicated and isolated exception handling for distinct parts of the system. This approach ensures that even in unexpected error scenarios, your API behaves predictably and informatively for its consumers. And to reinforce what we discussed earlier, writing automated tests for Spring apps remains non-negotiable. It's imperative to create a strong list of test cases that cover both positive scenarios, asserting proper function with valid input, and negative scenarios, testing error handling with invalid input or unexpected conditions.
So for Homeit, you'd have a comprehensive test suite for, say, the rental property controller. You'd use mockmv to perform requests and assert status codes and JSON paths for both successful creation and retrieval of properties, and critically, for field validation. For instance, testing if a landlord ID is missing, asserting that you get a 400 BAT request. This deep dive into designing robust Spring APIs, from layering to error handling, raises an important question. How do we ensure our data is handled robustly and efficiently within this well-designed architecture? Because without data, there's no Homeit.
Handling data and evolving your microservice.
All right, we've thoroughly explored how to structure Homeit services and handle errors gracefully. Now, let's dive into the persistence layer, which is, of course, crucial for any application storing data. Spring's incredible flexibility in managing database connections and interactions is truly a standout feature here.
The core concept that Spring champions, and the book articulates beautifully, is decoupling persistence. Spring's design philosophy actively encourages writing persistence repository interfaces that are fully separate from the code, specifying the actual databases or ORM implementations. This means the same data management code can work seamlessly with different database instances of the same type, like various SQL databases or different NoSQL providers, with minimal or no changes, just by updating a few configuration properties. This modularity is a huge win for adaptability, testability, and future-proofing your Homeit microservices. When it comes to data handling, the book highlights a critical choice: non-reactive blocking versus reactive non-blocking. Non-reactive blocking. In this traditional model, each database I/O operation blocks the executing thread. This is perfectly suitable for many Spring web applications without exceedingly high concurrent request volumes, perhaps up to thousands per second.
The excellent news here is that Java's new virtual threads, a significant advancement, can dramatically speed this up, making traditional blocking models much more efficient and scalable by allowing millions of virtual threads to run on a smaller pool of platform threads. This potentially lets you stick with the simpler, more familiar programming model for many high concurrency needs: reactive, non-blocking. In this model, I/O operations don't block threads. Instead, the code registers a callback and releases the thread back to the pool, allowing it to be shared across thousands of other requests. The code then resumes when the data arrives. This is absolutely essential for Spring Web Flux applications, offering higher concurrency and throughput for specific I/O-bound workloads. The trade-off is often between ease of understanding and development. Non-reactive is generally simpler and more linear, and achieving maximum concurrency throughput for extreme I/O-bound tasks, where reactive excels. With a virtual threads, that decision matrix has become far more nuanced.
For SQL databases and microservices, SQL databases are unparalleled when it comes to data integrity.
offering robust transaction capabilities and strict constraints. This makes them ideal for critical data like home, its financial transactions, or core rental proposal states. When organizing databases in a microservice architecture, the ideal, though often complex, approach is a separate database per microservice. This ensures true independence and prevents tight coupling. However, this introduces complexity for transactions impacting multiple services. 2. A home tenant payment needing consistency between payment, rental proposal, and notification services. An alternative is separate schemas in a single database instance, which simplifies backup and maintenance for the entire database, but can lead to performance burdens on that single instance if one microservice becomes a bottleneck. The decision always comes back to your specific functional and non-functional requirements: who accesses data how frequently, and what are the user wait time expectations.
That brings up a practical point for developers. What about a local development database for quick testing and iteration? Spinning up a full Postgres instance just for local work can be cumbersome.
That's a common need, and the book shows how to easily add support for a dev database like H2. H2 is a lightweight, in-memory, open-source Java database that's perfect for rapid prototyping and local development. By simply enabling spring.h2.console.enabled and setting spring.datasource.url in your Spring Boot application properties, developers gain a full SQL terminal directly in the browser. This makes it incredibly easy to connect to the in-memory H2 database and run SQL queries to check the state of your persistence layer, perform quick data manipulations, and rapidly iterate during development. When it comes to defining entities to be persisted, Spring JPA, Java Persistence API, uses various powerful annotations. At entity marks a class as a JPA entity for persistence, at table maps it to a specific database table, at a high designates the primary key, and a column provides details for individual columns. Lumbox at data annotation simplifies boilerplate code like getters and setters, keeping your entity classes clean. Spring validation annotations like at not null and at note empty are used directly on entity attributes for immediate data integrity checks. For HomeIt, the rental property entity is demonstrated effectively, showing how you can use a UED as its ID, along with landlord UED, name, and rent. Interestingly, the book showcases how the address can be stored as an embedded JSON object using @lob and @convert, which highlights Spring's flexibility in schema design beyond simple flat tables. Moving to how you interact with that data, it's a choice between ORM, object relational mapping, versus raw SQL and Spring data. ORM, primarily through packages like Hibernate via JPA, inspects your entity classes to automatically generate SQL queries for table creation and basic CRUD, create, read, update, delete operations. This is generally easier to use, offers cleaner APIs, and boosts developer velocity. Raw SQL using JDBD template or name parameter JBBT template means you're directly writing and managing SQL queries. This often offers higher performance due to fine-tuning opportunities, but it's more complex to write and maintain. The trade-off isn't just ease versus performance, it's about developer velocity now versus optimization debt later. If you pick ORM for that quick win, understand that when performance does become a critical concern, swapping to raw SQL isn't just a flip of a switch. It can be a significant refactor, especially for complex queries or highly optimized paths. The book's implied lesson here is to always prototype the most critical, performance-sensitive paths early on. Even if the rest of your application uses ORM, measure, then optimize. The book highlights JPrepository as your go-to SQL interface for ORM. It's an incredibly powerful interface that provides common CRUD operations, save, find by, delete by, without you writing any boilerplate code. For custom queries, you can simply declare method names based on property names. For example, find by landlord, ident, addressity, and rent between, and Spring Data will automatically generate the SQL for you. IDEs like IntelliJ even provide code completion for these method names, making development blazingly fast. For more complex custom queries that transcend simple property-based lookups, you can use the @query annotation with JPQL, JPA query language. However, it's important to be aware of limitations. JPrepository can introduce potential performance issues with very large tables, queries on non-indexed columns, or highly complex join operations if not carefully managed, or if underlying database tuning is neglected.
And for high-volume data, you can't just return everything at once, right? That's a recipe for disaster.
Exactly. Paging results for high-volume data is an absolute necessity. When querying large result sets like listing all HomeIt properties in California, paging mechanisms returning data in manageable chunks are crucial. This prevents server overload, reduces network traffic, and significantly improves user experience by delivering results incrementally rather than making users wait for an entire massive dataset to load. The book also covers using multiple service implementations and transactions. If an interface, such as rental property service, has multiple concrete classes, for example, one implemented with JPA, another with raw JDBC for performance reasons, Spring's that qualifier annotation allows you to explicitly inject a specific implementation. For transactions, the @transactional annotation is a lifesaver. You can simply annotate a method, and Spring ensures atomicity. All database operations within that method either succeed entirely or fail entirely, preventing inconsistent states. The book discusses its various parameters for nuanced control over transaction propagation, isolation, and rollback rules. Finally, the Entity Manager is briefly mentioned as a low-level bean for managing database connections and queries, which can be injected directly using a persistence context for fine-grained control when JRepository isn't enough. This deep dive into persistence truly shows the incredible power and flexibility Spring offers for data management. It allows Homeit to choose the right tool for each data challenge. But with all this crucial data flying around, this raises an important question. How do you secure those crucial interactions between services and users? Because security can't be an afterthought.
Securing services with Spring Security and Oath 2.0.
Okay, we've got Homeit services designed, and our data handling is robust. Now we tackle a non-negotiable paramount aspect of modern systems security. This chapter introduces Spring Security and Oath 2.0 as an incredibly powerful combination for building secure services, especially in a microservice architecture.
First, it's absolutely vital to understand the security areas in your application within a distributed microservice architecture. The book maps out typical vulnerabilities you must protect against at every layer. 1. Client application to API gateway. All external communication must use HTTPS to encrypt data in transit. 2. API gateway to microservices. Secure internal routing and authentication authorization enforcement at the entry point. 3. Microservices to databases. Ensuring data at rest, encryption, and in-transit secure connections is protected. 4. Microservice to microservice communication. Secure internal calls, often using tokens or MTLS, mutual TLS. 5. Authentication. This is about verifying who a user is, proving their identity. 6. Authorization. This is about determining what that authenticated user can do, defining permissions. An attacker, for example, could try to spy on user connections, or an authenticated Homeit tenant might attempt to perform an unauthorized operation, like trying to delete a landlord's user account. Security needs to be considered and implemented at every single layer, not just at the front door. A key protocol here is OAuth 2.0. It's crucial to understand that OAuth 2.0 is primarily an authorization framework, not an authentication protocol. This is a common misconception. It's for delegated access, allowing a user to grant a third-party application limited access to their resources without ever sharing their actual credentials. The book presents two primary use cases that are highly relevant to Homeit. Use case 1. System A accesses System B's resources. Think of Homeit registering a new user by having them authenticate on Google. You, as the user, grant Homeit limited access to your Google profile details without ever giving Homeit your Google password. Use case 2. System A accesses its own resources. This is the more common microservice pattern for internal systems. A Homeit client application, like their mobile app, authenticates the user and then obtains a token to access Homeit's own backend microservices. This is where most of our focus lies for internal communication. The basic service types in OAuth 2.0 are resource owner, the entity owning the protected resources, example, Google for your documents, or the end user for their own Homeit data, authorization servers. These are the services responsible for issuing access tokens after a successful authentication and consent from the resource owner. Client application. This is the application, for example, the Homeit mobile app, that allows users to log in and request access tokens on their behalf.
And what about JWTs, JSON Web Tokens? They seem to be absolutely everywhere in modern security for microservices. How do they fit into this picture with OAuth 2.0?
JWTs, JSON Web Tokens, are essential to stateless microservice security. They are compact, URL-safe means of representing claims, statements about a user or entity. The real beauty and utility for microservices is that they are stateless and self-contained. This means once a token is issued, a microservice can validate it locally without needing to make a network callback to a central authentication service for every single request. This is critical for performance and scalability in distributed systems. A JWT has 3 distinct parts, typically separated by dots. Header specifies the token type, always JWT, and the signing algorithm used, for example, HS256 for symmetric key, RSA for asymmetric. Payload. This is where the claims reside information about the user or entity. And this includes standard claims like IS, issuer, subject user ID, expiration time, EIT, issued at time, and often public user details like name, email, groups they belong to, or specific permissions. Signature. This is the crucial part for integrity and authenticity. It's created by signing the encoded header and payload with a secret key, symmetric like HS2586, or a private key, asymmetric like RSA. The authorization service verifies the signature to ensure the token hasn't been tampered with and was indeed issued by a trusted source. The book also discusses different architectures for validating tokens. You can use symmetric keys, simpler, but the same key is used for both signing and verifying, which can be a security risk if compromised, or asymmetric keys, more secure, with a separate private key for signing and a public key for verifying. A key challenge with stateless JWTs is token lifespan and revocation. Short-lived tokens are more secure against theft but increase client load due to more frequent renewals. Revocation is tricky in a stateless system as there's no central session to invalidate. This often requires a blacklist or deny list stored in a fast database or cache for revoked tokens. The drawbacks of JWTs include the need for robust key management, solid revocation strategies if keys are compromised, and the increased vulnerability of long-lived tokens if they are stolen.
So how does HomeIt actually implement its security using Spring Security in these concepts? What does the code look like to tie it all together?
The book walks through implementing HomeIt security with Spring Security. The core is setting up a web security config class. This class is annotated with @configuration and @enable web security, signaling to Spring that this class contains your security configuration. Inside, you'll typically see disabling CSRF, cross-site request forgery, and CORS, cross-origin resource sharing, filters initially. For API development, this often simplifies things, though in a real production scenario, CORS would be tightly restricted to known client origins for security. Authorize HTTP requests. This is where you define fine-grained authorization rules. For HomeIt, you might set users register and users token to permittal, meaning anyone can access them without authentication to get a token. All other endpoints, however, would require authenticated users, session management, stateless. This configuration is absolutely crucial for microservices. It explicitly tells Spring Security that the service does not persist session objects to track user state on the server. Instead, it relies solely on the JWT token provided with each request for user identification and authentication. This design is critical because it avoids race conditions in a distributed system and significantly simplifies horizontal scaling across many independent microservice instances. Several service components for authentication support this Spring Security setup. User service. This handles core user management, including user creation, finding users by their email, find by email, and securely validating passwords, validate user, using a password encoder for hashing, client service. A simpler service in the book's example to validate client-side and client secret, which could be extended for managing client-specific tokens for third-party integrations. Scope service. This provides the JWT scope, which defines the specific permissions granted to the user within their token. JWT service. This is the heart of token creation, responsible for securely generating asymmetric key pairs and creating JWT tokens, get JWT token, with all the necessary claims, payload data, signed correctly. The HomeIt authentication flow practically demonstrates this. You can use a curl command to register a new user and then create a JWT token for that user using the password grant type. The token is returned, and any subsequent request to protected endpoints would include this token in the authorization header. This comprehensive setup ensures it has robust, stateless security for its microservice architectures, allowing for efficient, scalable authentication and authorization.
What's fascinating here is how this allows HomeIt to scale securely. Once a token is issued, individual microservices can validate it locally without a constant, high-latency round trip to a central authentication server, providing immense efficiency and resilience. But that raises another critical point. Once they're secured, how do these services actually talk to each other within the HomeIt ecosystem?
Communicating between services with Spring Web Flux and message queues.
All right, we've successfully designed and secured HomeIt's services. Now comes a critical question for any microservice architecture. How do they talk to each other efficiently and securely? This chapter dives into sophisticated inter-service communication patterns, going beyond simple direct calls.
The book starts by addressing a fundamental concern in complex systems: service communication and coupling. The stark reality is that direct REST API calls between services, while seemingly simple at first, lead to heavy coupling. As the number of connected services grows exponentially, it becomes increasingly difficult to develop, deploy, and evolve them separately and independently. Imagine Home, its rental proposal service, directly calling the rental property, messaging, and payment services for every operation. This creates a dense web of dependencies, resulting in a lot of complex code to read, edit, and maintain. Changes in one service require careful coordination with many others, increasing complexity and making deployments risky. The ultimate goal, therefore, is to decouple calls, significantly reducing the number of direct dependencies between services to improve agility and resilience. This is precisely where event-driven architectures, EDA, shine brightly. EDA excels at decoupling. Instead of direct calls, services communicate asynchronously by publishing and subscribing to events via an intermediary, typically a message broker like Apache Kafka. Queues versus topics. The book clarifies the distinction. A queue is point-to-point. A message is consumed by only one listener. A topic, on the other hand, operates on a publish-subscribe model. A message published to a topic can be consumed by multiple interested listeners simultaneously. Message types. There's a trade-off here. Fat messages contain the full state of the object, reducing the need for subscribers to make follow-up lookups. However, this can increase coupling, a concept the book refers to as domain spilling, where one service's domain knowledge leaks into others. Thin messages only contain an ID or minimal context, requiring subscribers to call back to the publisher for full data. This maintains strict domain separation but increases network calls. Business versus entity-driven events. A crucial design decision. You must decide if events are about specific entities changing, for example, a rental proposal created event, or broader business processes, Beige rental proposal approved business event. This influences the granularity, content, and consumer base of your messages.
So how does Apache Kafka, which we hear so much about, fit into this event-driven world for Homeit?
Kafka is a ubiquitous and powerful distributed streaming platform often used as the central nervous system in EDAs. Its core concepts are essential to grasp. Publishers, producers. These are the services that send messages to Kafka topics. Consumer subscribers. These are the services that read messages from Kafka topics. Topics. These are categories or feeds to which records are published. Topics are logically divided into partitions for horizontal scalability and parallelism. And critically, messages are ordered within each partition. Consumer groups. Multiple consumers can read from the same topic, with Kafka ensuring that each group consumes a different set of partitions, allowing messages to be distributed efficiently among group members. For practicality, the book even briefly mentions how straightforward it is to install Kafka for development and run a console consumer to view events in real time. This is an invaluable tool for debugging and verifying your event streams as you develop Homeit services. The chapter also touches on using MongoDB for NoSQL persistence. It introduces MongoDB as a flexible, document-oriented NoSQL database. For services built with Spring WebFlex, Spring Data MongoDB, specifically Reactive Mono Repository, enables asynchronous, non-blocking database operations. This makes it a natural, high-performance fit for reactive services. For Homeit, the rental proposal repository could use Reactive Mongo Repository to asynchronously save and retrieve rental proposal objects without blocking threads.
And speaking of Spring WebFlex, how do you actually write a high-performance responsive service with it for Homeit that can handle a lot of concurrent activity?
Spring WebFlex is the key to building high-performance, non-blocking services. It relies fundamentally on reactive programming with Mono and Flux. Mono represents a stream of 0 or 1 item. Think of it as an asynchronous container for a single object or just a completion signal. Flux represents a stream of 0 to n items. This is for collections of objects that arrive over time. The profound benefit is that these enable non-blocking I/O, which is absolutely vital for handling thousands of concurrent requests or long-running I/O operations without blocking threads. WebFlex natively allows streaming object collections, meaning HTTP clients can consume objects incrementally from a Flux stream. For example, Homeit could query a large number of properties from MongoDB and return results little by little to the client, improving perceived performance and reducing memory overhead. Let's look at our event-driven sample in Homeit. Here's how it stitches together. The rental proposal service acts as a publisher. When a new proposal is saved or a rental round is updated, it publishes a rental proposal event to a Kafka topic. Let's call it proposal topic. Crucially, the rental property service acts as a consumer. It subscribes to these notifications. When it receives a rental proposal event, it updates a score or popularity metric for the associated rental property in its own database. This way, other customers browsing properties can immediately see how popular a property is without the rental proposal service needing to directly call and update the rental property service. That truly demonstrates the power of decoupling and asynchronous communication in a real-world scenario.
That's a great illustration of decoupling. But beyond just communication, the book then circles back to security, showing how to add even more security to Homeit authentication.
specifically for inter-service communication. How does that work with token revocation, which can be tricky in a stateless system?
Excellent point. It introduces a separate revoke token service built efficiently with WebFlex and its router config for high concurrency. This service is dedicated to managing a blacklist of revoked JWT tokens. Now, the rental property service, acting as a consumer and needing to validate incoming requests, uses a custom token revocation filter and a REST template revoke token service internally. This component sends an HTTP request to the remote revoke token service to check if a token has been revoked. This means that in addition to simply validating the JWT signature, ensuring it hasn't been tampered with and was issued by a trusted source, the token is also checked against the revocation list. The HOMIT authentication flow diagram in the book, Figure 9.1, clearly illustrates this. User authentication leads to JWT token issuance, and then critically, JWT token validation includes an explicit call to the revoke token service before authorization is finally granted. This is crucial for instantly invalidating compromised or stale tokens, even in a stateless microservice world. This robust architecture also allows for incredibly comprehensive extending end-to-end tests. For HOMIT, an example end-to-end test sequence would be quite revealing. First, a landlord creates a user and obtains a token. Simultaneously, a tenant creates their user and obtains a token. The landlord then successfully creates a property. The tenant retrieves that property. Then the tenant fails to create a property, as expected since only landlords can. Next, you verify the landlord's token is not yet revoked. Then, you actively revoke the landlord's token via the revoke token service. And finally, the landlord fails to create a property because their token is now revoked. This validates the entire communication, authentication, authorization, and security chain across multiple services, truly testing the resilience of your design.
This shows how choosing the right communication pattern, whether direct calls or event-driven, profoundly impacts system design, scalability, and resilience for HOMIT. But even with the best planning and design, things still go wrong in production. So once these services are built and talking, how do we manage them once they're deployed to a cloud environment?
Launching your self-organizing microservice cloud.
We've designed HOMIT services, secured them, and enabled sophisticated communication between them. Now we transition to the operational side of microservices, which is just as critical as the development. This chapter focuses on how to configure, launch, and manage these services efficiently in a cloud environment using Spring Cloud. It's about bringing order, automation, and stability to a fleet of independent services.
A fundamental aspect of managing any production system is how to produce your service logs. You absolutely need to move beyond simple system.out.println for debugging. Structured logging is paramount for troubleshooting distributed systems where a single request might traverse many services. The book detailed common log levels and their precise purpose. Trace. The most detailed for tracing execution flow through your code. Debug. Key variable values and flow details, primarily for debugging during development or in staging. Info. General application progress, major milestones, and non-critical events. E.g., user logged in, property created successfully. This is your primary level for monitoring healthy application flow. Warn. Unexpected situations or potential issues that don't immediately stop the application but indicate something might be amiss. For example, a client sending a malformed request resulting in a 400 bad request, or a third-party API returning a non-fatal error. Error. Application can continue, but a specific operation failed, e.g. an exception caught, a database connection failed for one transaction. Fatal. A severe, unrecoverable error indicating this application likely cannot continue and requires immediate attention. You can configure log levels in application.properties, EAG logging.level.root info for general output, logging.level.org.springframework.webdebug for detailed web request logging. You can set specific package levels for fine-grained control, which is vital for transparently understanding what's happening in your live environment without drowning in irrelevant details. Next, how to organize your property files is crucial for configuration management across different environments, development, staging, production. Spring Boot offers incredibly flexible ways to manage these external properties. 1. Placing application.properties or application.eml directly in the same directory as your JAR file. These will override defaults compiled into the JAR. 2. Using specific profile files, e.g. application-prod.properties, application-dev.properties. These are activated by the spring.profiles.activeSystemProperty or environment variable. For HOMIT, each microservice might have its own rental property-microservice-dev.properties and rental property-microservice-prod.properties files, allowing environment-specific settings for databases, external APIs, etc. 3. Setting properties via command line arguments, spring.profiles.activeprod server.port 80.081. 4. Using OS environment variables. These methods allow you to manage application properties external to the code, making deployment and environment-specific configuration changes much easier without rebuilding your application.
This sounds like it could still involve a lot of manual configuration if you have many microservices. How does Spring Cloud help automate the launch and connection of these services, essentially creating a self-organizing cloud for Homeit?
That's precisely where setting up services using Spring Cloud comes in. Spring Cloud is not a single product, but a comprehensive suite of tools designed to simplify microservice launches and connections, addressing the complexities of distributed systems. Its key features provide crucial infrastructure for Homeit Config Server. This provides a centralized service for hosting configuration files for all your microservices. Instead of deploying application-prod.properties with each service, they all pull their configuration from this central server, allowing dynamic updates without redeploying microservices. Discovery Service, Eureka. This is essential for dynamic microservice environments. It helps services find each other automatically, regardless of their dynamic IPs and ports, which change frequently in cloud environments. A Spring Boot application simply needs the add-enable discovery client annotation to register itself with Eureka, announcing its presence and capabilities. API Gateway. This provides a unified public entry point for external clients to access your entire fleet of microservices. It handles routing requests to specific microservices and can manage crucial cross-cutting concerns like authentication, rate limiting, and request transformation before the request ever hits your individual microservices. With a discovery service like Eureka in place, Homeit's microservices can now engage in self-discovery. Instead of hard-coding IPs or ports, microservices can call each other simply by their registered service name, for example, albiat rental property-microservice. The pound prefix means Spring Cloud automatically provides client-side load balancing, intelligently distributing calls among multiple running instances of the same target service. This significantly improves resilience and scalability as new instances can be added or removed dynamically. Implementing the API gateway is highly configurable. For Homeit, your API gateway configuration would define public paths like proposals and properties and map them to internal services using URI, alb.rentalproposal-microservice, or URI, alb.rental-property-microservice. Attributes like IDID, a unique route ID, URI with the pound for discovery, predicates for path matching like path proposals, and filters like strip prefix 1 to remove path segments from the URL before forwarding are used. The real power here is that the API gateway is dynamically updated as services go up or down through the discovery service, ensuring powerful and resilient routing even in a constantly changing cloud environment.
This is how you bring order and automation to a fleet of microservices, ensuring they can find and communicate with each other dynamically and reliably. It's truly building a self-healing cloud. But even with the best planning and robust infrastructure, things will go wrong. How do we optimize Homeit services? And more importantly, how do we design them to recover gracefully from failure?
Optimizing your services.
We've covered designing, securing, communicating, and managing our services in a microservice cloud. Now, for the grand finale of this deep dive, we confront the stark realities of production systems. Failures happen. This final chapter is all about preparing your system to be resilient, fault-tolerant, and optimized for real-world chaos. It's about designing for failure as much as for functionality, because in production, things will go wrong.
The first principle, and a crucial one, is setting performance expectations coupled with the powerful mantra, launch early, optimize later. Don't strive for a perfectly optimized system from scratch. Premature optimization is incredibly expensive, time-consuming, and often completely unnecessary. You should only optimize against clear, measured issues identified in production environments. When troubleshooting a performance bottleneck, the book advises a systematic approach. Break down your architecture into its individual components, test each separately, and trace network hops to pinpoint the exact source of the bottleneck. Is it a slow database query, an inefficient algorithm in your service, or simply network latency between services? Measure, then act. A powerful technique for speeding up Homeit's services is using caching to speed up access. Caching involves storing frequently accessed data in a faster in-memory store, like Redis or Memcached, to reduce the load on your primary database. Spring caching, easily enabled with @enable caching, allows you to apply caching directly to our methods using annotations like @cacheable to cache method results, @cacheput to update cache data when the underlying source changes, and @cacheevict to remove data from the cache when it becomes stale or is deleted. The trade-off is clear. Caching dramatically improves read performance and reduces database stress, but it introduces complexity around cache invalidation and ensuring data consistency across distributed caches. When failures inevitably occur in an event-driven system, recovering from failures with dead letter queues, DLQ, is a vital pattern. A DLQ is a separate queue where messages that couldn't be processed successfully by a consumer are automatically moved. The immense benefit is that it prevents poison pill messages from blocking your main processing queues, allows for manual inspection of failed messages to understand the root cause, and provides an opportunity for reprocessing once the issue is resolved. This significantly enhances overall system resilience. For real-time visibility into home it's running services, real-time service monitoring with Spring Actuator is indispensable. Spring Actuator provides production-ready features directly embedded into your application, allowing you to monitor and manage its state without needing to dig deep into logs. You get endpoints for health checks, application metrics like CPU usage, memory, request rates, environment information, and more. This proactive monitoring is key to quickly identifying issues before they impact users.
And what about proactively handling faulty services before they completely break the system or cause cascading failures?
That's where Resilience 4J comes in. It's a lightweight, battle-tested fault tolerance library for Java, implementing various crucial patterns. Circuit breaker at circuit breaker. This is perhaps the most critical. It prevents an application from repeatedly trying to perform an operation that is likely to fail, for example, calling a downstream service that's unresponsive. After a configurable threshold of failures, failure rate threshold, or slow calls, the circuit opens trips, redirecting all subsequent requests to an immediate fallback implementation, preventing cascading failures. After a wait duration in open state, it enters a half-open state to send a few test requests and see if the faulty service has recovered. For HomeIt, if the revoke token service goes down, the circuit breaker on the rental property service would open, and its token revoked would immediately return a default false, token not revoked, allowing the property service to continue functioning without blocking. Rate limiting at rate limiter controls the rate of requests sent to a service to prevent it from being overwhelmed, protecting it from denial of service attacks or runaway clients. Retry at retry automatically reattempts failed operations a specified number of times, useful for transient network errors. Bulkhead at bulkhead isolates failures in one part of a system by limiting concurrent calls to a service, preventing a failure in one component from consuming all resources and affecting other healthy parts. For instance, limiting concurrent calls to an external payment gateway. The trade-off here is that applying multiple Resilience 4J annotations on the same method requires thorough testing to understand their combined, sometimes complex, behavior. Another critical aspect is preventing race conditions with a SQL trick. In a distributed system with multiple service instances, traditional microservice-level solutions like synchronized blocks, which only work within a single process, or even distributed locks, which add their own complexity, don't always reliably prevent race conditions across different instances. For example, if two HomeIt tenants try to accept the same rental proposal simultaneously, it could lead to an inconsistent state where both think they've secured the property. The most reliable solution often comes down to database locks, specifically pessimistic locking, using a SQL command like selectup for update. This command locks the selected rows in the database, preventing other transactions from modifying them until the current transaction commits or rolls back. The first transaction to acquire the lock proceeds and others wait. It's simple, highly effective, and handles concurrency at the lowest, most reliable level. The trade-off, however, is that it can introduce bottlenecks if not used carefully, as it's a blocking operation, potentially reducing concurrent throughput on those specific rows. To deal with a sudden surge of requests, the throttling pattern is a robust way to manage bursts of traffic and prevent system overload. The mechanism involves 1. Accepting all requests initially, returning a quick request received response to the user. 2. Queuing these requests, for example, in Kafka or a dedicated message queue. 3. A separate background worker then consumes requests from the queue at a controlled, sustainable rate. 4. Users receive updates, for example, email or in-app notification as the requests are processed. The immense benefit is that this pattern spreads peak load over time, preventing your system from being overwhelmed, failing, or slowing down under heavy, unpredictable traffic. Finally, as a last line of defense, the book discusses recovering from failures by using an audit job. This is a periodic, often batch job that scans system data to identify and rectify inconsistencies that might arise from partial failures or subtle race conditions not caught by other mechanisms. It's about building resilience not just in real time, but also asynchronously, ensuring data integrity and consistency over time.
Okay, that's a comprehensive look at optimizing and building resilient services, taking HomeIt from idea to production ready. It's clear that designing for failure is just as important as designing for functionality, because in the real world, things will go wrong, and your system needs to gracefully handle it. Hashtag, tag, tag, outro, outro. And that brings our deep dive to a close. What an incredible journey we've taken with Homeit. From understanding those abstract product requirements, meticulously defining core domains, to building resilient, high-performance, and secure Spring microservices that can scale in the cloud and recover from failure. The Homeit case study truly brought these practical, job-ready insights to life, showing how each piece fits into the larger, complex puzzle of system design.
Indeed. The core message reinforced throughout this entire exploration is that system design is fundamentally about making informed trade-offs, thinking holistically about every layer, and applying the right tools for the job based on specific requirements. It's about considering performance, security, and scalability not as afterthoughts, but as integral parts of the design process from the very outset. It's a continuous learning curve, but these principles provide a solid compass.
So, armed with these powerful concepts, the strategic blueprint for Spring-based systems, and the lessons from Homeit's journey, what system are you going to build or improve next? What new design challenge will you tackle with this deeper understanding? Perhaps applying some of those clever throttling patterns or circuit breakers. We've shown you how to best do it. Now it's your turn to apply it. Thank you for joining us on the deep dive. Until next time, keep diving deep into the knowledge that matters.